let's try and understand what we mean by the sampling distribution of the sample proportion. A sampling distribution is the distribution of all possible values of a statistic, like p hat, using the same sample size selected from a population. So what does all that mean? Well, if you look at this is a large pond and it's got lots of healthy fish happily swimming around. But what would happen if, say, a nuclear blast occurred or a chemical spill happened nearby to this fish farm? Well, clearly some of the fish would die, some of them would live, while others would become freaky. In other words, we'll have freaky fish. Notice these freaky fish have 3 eyes and 2 tails and some pretty mean looking teeth. So whenever I talk about freaky fish, I'll be referring to this character here. In other words, fish that are a bit different. So if you were a fish farmer and you noticed that some of your fish were becoming freaky, you would clearly become worried and want to know, well, what proportion of fish on my farm are freaky? So how would you go about estimating that? Well, the first thing we would need to do is to understand the sampling distribution of the sample proportion. And what we'd have to do is get a bucket and go and collect, let's say, a sample of 20 fish in this bucket. That would be okay and quite straightforward to do. Let's just go get 20 fish. We could then count the number of freaky fish in that bucket, and from that we can now calculate the proportion of freaky fish in the bucket. This first bucket that we caught with 20 fish in it, and I'll denote that p hat for the proportion for the sample and 1 being the first bucket. The way we'd calculate p hat is simply the number of freaky fish we observe in the bucket divided by all the fish in the bucket. So if we had 6 freaky fish over 20 in the bucket, 6 over 20 would be 30%. So the proportion of freaky fish would be 30% or 0.3. So in other words, p hat is simply a fraction. So having done that, if we want to understand the sampling distribution of the sample proportion, we'd have to put all the fish that we first caught back in the pond. Why? Because we now have to go and catch another sample of 20 fish from this same pond. But what we're looking for is a different combination of fish, because ultimately we want to try and find all possible combinations of 20 fish from this fish farm pond in order to be able to plot the sampling distribution of the sample proportion. So in other words, if I had my first bucket of 20 fish and I saw 1 freaky fish in it, I could calculate p hat for the first bucket. Put all the fish back, get another sample of 20 fish, and there might be 2 freaky fish in there. That would give me the second sample proportion. Put all the fish back, get a third bucket of 20 fish, and maybe this time there's no freaky fish in the bucket. So to get this idea of the sampling distribution proportion, I have to continue catching 20 fish until I get the last possible bucket and last possible combination of 20 fish in that bucket. So in here I've just put 1 freaky fish. But nonetheless, that's going to be a very long and time-consuming process if, let's say, there's 10,000 fish on my fish farm. It's practically impossible to do it. So why are we even thinking about it? Well, theoretically, it is possible to do what we're talking about here. And by theoretically doing this, we can generate what's called the sampling distribution of the sample proportion. So if I continued this process, I could then plot the values that I find and generate this idea of sampling distribution of a sample proportion. Remembering sampling distribution is nothing more than spread. So we're looking at the spread of these sample proportions. So let's consider plotting p hat on the horizontal axis, the sample proportion, and let's say it goes from 10% being freaky all the way up to 50% being freaky. And on the vertical axis, let's just plot the frequency, the number of times we observe a certain proportion of freaky fish in a bucket. So effectively, let's just build a histogram. So the first observation of freaky fish in my first bucket of 20 fish, let's say, is 15% of freaky. I put the fish back, get another sample of 20 fish, and this time 30% of the fish in the bucket are freaky. Put the fish back, get another sample of 20 fish, and 40% are freaky. So every time I observe a proportion of freaky fish, I'm just plotting a bucket. So I continue doing this, and I count how many times I observe, let's say, 30% being freaky, and at this point I've already counted 3 buckets of freaky fish that represent 30% of freaky fish in the bucket. So I keep going and continue to find different combinations of samples. These are all different sample combinations, and ultimately it stacks up into a shape. Let's just stop here. I would have to continue on many, many more buckets if I had 10,000 fish in this pond. But let's assume at this point that the population proportion was 30%. It's 30% of the fish in the pond are freaky. I don't know that necessarily, but let's just assume they are here. It wouldn't be hard to imagine that if you went and got a bucket of 20 fish, many times the sample proportion should plot somewhere around here, so that ultimately the distribution that you end up with looks as though it's normally distributed, with a lot of the fish, or the proportion of freaky fish, concentrated towards the middle, and very few fish concentrated out towards the ends. In other words, it's pretty unlikely to get no freaky fish in a bucket if the population proportion of freaky fish is 30%. And it's pretty unlikely that half the fish in the bucket are going to be freaky if only 30% of the fish in the population are freaky when you get a sample of 20. So what we have here is a spread or distribution of sample proportions. So this shape that we're plotting here is what we call the sampling distribution of the sample proportion. And it looks as though it's normally distributed. So the question is it? Well, it turns out the sampling distribution of the sample proportion is a very good approximation to the normal distribution, provided certain assumptions are met. But nonetheless, what we now see here is what we call the sampling distribution of the sample proportion.